Let's take a closer look at types in Haskell. Early on, we wrote some functions on lists, which we defined as functions over lists of integers. For instance, we wrote this function length, which inductively assigns 0 to the length of the empty list and adds 1 for each element in the list. We also wrote this similar inductive function to reverse a list. And finally, we wrote the reverse of the head function, which takes the last element, the tail function, which takes the first segment of the list, leaving off the last element. Now, all of these functions have one thing in common, which is that they don't actually bother about the values in the list. Right? So it's really a structural property of the list. The length of the list really just depends on how many elements there are. When you reverse the list, you just take the elements in the list and reverse the order. Similarly, when you take the initial segment of a list, you just drop the last element. So in all these things, you can actually assume that similar things will work regardless of the type of element in the list. So if you think of a list as a list of boxes in some sense, right? And then if you need a value in the list, you need to open the box. So none of these functions actually need to open the boxes. They can just move the boxes around or select a few of the boxes or one of the boxes and so on. So it would be nice if we could assign within the type system that Haskell uses for each function a type which will allow a function to work across multiple input types like this. So we would like reverse, for instance, to work on lists of int or lists of float or even lists of lists, so long as the underlying value is a uniform type. So in Haskell we use type variables, usually A, B, C, letters like these, as placeholders for type. So if we say that a function takes as input type A, it means A can stand for any input. And if A stands for any input, then if we put square brackets around A, then we denote a list of that type. So if we go back now to our list functions, what does myLength do? MyLength takes any list and produces the length. The length is a number, so the output type is int. The input type is unconstrained. It can be a list of any type of A. So we write the type as list of A to int. Reverse, on the other hand, takes a list and produces another list. So once again, it takes an arbitrary list, but it produces a list of the same type. So it's important that the A on the left and the A on the right are actually the same A. It means that if I give it an input of list of int, it will produce an output which is a list of int. If I give it a list of float, it will produce a list of float as output. You cannot change the type, but the type itself is not fixed in advance. And finally, if you look at myInit, right? So what it does is it actually produces, so there's a small mistake here. So it takes again a list of A and produces a list of A. And if we wrote a function like head, for instance, then it would take a list of A and produce a single value of type A. Right? So the important thing to note is that if I have a variable, then wherever it appears in the type, it must be instantiated by the same type. So let us digress a little bit about notation of operators and functions in Haskell. So we have seen arithmetic operators like plus, minus, divide. We also have Boolean operators like or and. So we could have x and y and so on. So these are operations which operate on two values, but we write them in this infix notation. That is, we put the operation in between the arguments, right? So we have two arguments and the operator comes in between. So the operator is, this is said to be infix. On the other hand, we have seen functions which are predefined like div and mod, which are written as functions. In other words, you write the name of the function and then you write the arguments. So this is what is called prefix notation, because the function comes before the arguments. Now, sometimes you may want to switch between these two notations or two views. So in particular, we can take any binary operator which you have defined and make it into a function just by putting round brackets around it. So the operator plus can be written as a function by writing round bracket plus. So this expression plus 3, 5 is exactly the same as 3 plus 5 and so on, right? So in this way, we can use this notation to convert operators to functions. And we can also do the reverse, provided of course the function takes two arguments, because otherwise it's not clear what it means to be infix. Infix means it's between the two arguments. So if we have binary functions like div or mod, then we can use this reverse quote. This is the back quote key. This is not the normal apostrophe, but the back quote which you will find on your keyboard. So if we enclose the name of the function with these reverse quotes, then we can use them as operators. So if we want to say 11 mod 5 and not mod 11 5, then we write 11 backquote mod 5. Right? So here we've written 7 div 5, 11 mod 3, and so on. So this is useful in the sense that we have seen. Suppose we have written a function plus, which takes two integers and adds them. What we saw is that because of currying, plus actually consumes the arguments one at a time. So in an intermediate stage, when it has consumed the first argument, we have a new function which we can write called plus m, which actually takes whatever it takes as a second argument, namely the n, and it will add m to it. So m is now fixed, right? So in the same way, we can think of this using the normal plus operator. So m plus n is the same as this round bracket plus mn. So this round bracket plus is a function which is exactly like the PLUS plus we wrote above, which takes two arguments. And if it takes one of them, then it becomes the function plus m. So plus m adds m to its argument. So you can try this out in the Haskell interpreter in GHCI. So if you take something like plus 17 and you apply it to 7, then plus 17 will add 7 to 17 and give you 24. Right? So using the fact that we can convert operators to functions by using the round bracket, we can also get partially instantiated functions where one of the arguments has been fixed, and use these when we manipulate functions in Haskell. Now, manipulating functions in Haskell takes us to this notion of a higher order function. So in Haskell, there is no particular problem or specific thing that we need to do to pass a function as an argument to another function. So here is the most obvious function we could write like this. So we can take a function called apply, which takes two arguments and applies the first one to the second one. So it really reads the function as its first argument. It reads a value as a second argument and applies the function it gets to the value it gets. Right? So it just says given f and given x, return the value f of x. So here, for instance, if we say something like apply the function plus 17 to 7, then this should reduce by the application of plus 17 to 7 to the value 24. Right? This is the intention. So what is the type of this function? Well, the first argument is a function, and we want it to be possible to send all possible functions to apply. So if we make no assumption about the function, then it takes an input type and it takes an output type, which may be different. So a generic function f has type from a to b, where a and b are possibly different types. Right? So there's no constraint. A and b may be the same type, may be different types. We don't constrain it in any way. Now, given that f takes an input of type a and produces an output of type b, this constrains the type of x, right? Because x is now going to be passed to f. So f takes a's, so x must be an a, and the result must be a b, right? So the argument x and the output must be compatible with this choice. So this must be of type a, and this must be of type b. So this gives us the following type. So this function, so this is not f but apply. So apply takes as its first argument some unknown function f, okay, and it takes as a second argument a value to be passed to this function, and it produces an output which is the application of f to x, which, because f has type a to b, this is of type b, right? So apply has type from a function from a to b and an input of type a produce an output of type b. So higher order functions will turn out to be very useful. So here is a very familiar thing that you would have seen before. So suppose we want to sort a list of objects. At the heart of every sorting algorithm is a comparison between objects. So we need to take pairs of objects and order them in the right way. So in some situations, it might be important to know how to compare these objects. If we have pairs, then we use only one component, we use dictionary ordering, and so on. And also we might want to know in which direction to order them. Do we want to order them in ascending order, in descending order, and so on. So to be fully flexible, what we would like is that we have the sort function, and it should take actually two inputs. It should take the compare function and it should take the list, and then use this compare function to sort this list according to the sorting algorithm. So by changing the compare function, for instance, we can make it go from ascending to descending and so on. So this is a natural situation in which we pass a function to another function, and we will see other examples of this. So to summarize, Haskell functions, typically those we have seen which are structural functions on lists, like things like take the length or reverse it or take an initial segment or a final segment, can be polymorphic. In other words, they can operate on lists of more than one type. We have also seen that we can use this round bracket and the back quote to convert operations to functions, operators to functions, and vice versa. And finally, we have seen that in Haskell, it's no big deal to pass a function to another function. So we have higher order functions, so to speak, for free. And this is very useful. And we saw an example in the context of sorting, and we will see more examples in the lectures to come.